The last class we have introduced Fourier transform as a k of a function of f of x in its symmetric form as integration from minus infinity to plus infinity f of x e to the power minus I kx dx, and the inverse transformation was this. We have arrived at this result starting from the Parseval's equality. We have arrived at from Parseval's equality, which says that minus L to plus L integration of f modulus square dx is equal to delta, which is equal to 12 times n from minus infinity to plus infinity cn modulus square. This was our starting point, Parseval's equality, and finally we let L tends to infinity to get the Fourier transform. Here we have defined the Fourier transform as a limiting case of Fourier series when the range tends to plus minus infinity. The Fourier transform could as well be introduced as a special case of integral transform, which we have already discussed in the last class. Fourier transform can also be obtained from trigonometric Fourier series, which we shall take up later. Now let me discuss what happens to these transformation pairs when the function under consideration have a definite parity. In the case of trigonometric Fourier series, we have found that when fx is even, then bn's are 0, and one need to calculate only an's, and for odd function only bn survives. And in the form of complex Fourier series, we have seen that when the function is even, then Fourier coefficients cn's are pure real numbers, and when function is odd, cn's are purely imaginary. When the function under consideration have no parity, don't have no definite parity, then in trigonometric Fourier series both an's and bn's survives, and in complex form of Fourier series the c's are complex numbers. Now our interest is to see what is the simplification that we can achieve in case of Fourier transform when the function has definite parity. So we call, if f of x is even, then what happens? We define ak we divide the interval into two parts. We change this one as this. F of minus u e to the power d of minus u. So we have changed u as minus x, so Now this term, since it is even, f of u is u, and then we get this minus sign changes the limit. So this is f of u e to the power I k u du. Since this is a definite integral, since it is a definite integral, we can change u by minus u by x as well. So this term finally goes to, this one becomes 1 upon root 2 pi note that this is plus sign. So we write it as the second part remains unaltered. So the integration is basically plus I k x plus e to the power minus I k x dx. This is equal to 2 cos kx. So the result becomes 2 by pi 0 to infinity Now we see that a of k, this implies a of minus k is equal to plus a of k, as it is even. So a of k is even. Now so the summary is that when f of a is root 2 upon pi integration from 0 to infinity f of x cos of kx dx. Now we see what happens to f of x. It can be also divided into two parts. So first let me write the basic definition of f of x. Which can be written, since a of k is even, this can be written as following exactly the same procedure that I have adopted over it. This is the Fourier transform for an even function. So the summary is that I write it a bit. and f of so this is the simplification. What happens now? I ask the question: what happens when f(x) is odd? What simplification do we get from there? Let me start again from the basic definition. If f of x is equal to odd, then what happens? The a of k is minus infinity to plus infinity f of x e to the power minus I kx dx, which we write dx. For this part, we first change this f of minus u e to the power plus I k u d of minus u. Then since it is odd, it will be negative. This will be a negative sign, this will be there will be another negative sign, so makes it plus. So and when we interchange this limit, this becomes f of u e to the power I k u du, and since this u can safely be changed by x, we write it as, so the first term is written as dx. This part within the quantity within second bracket is twice I sine kx. And you see that ak is odd, a of minus k is equal to minus of ak. So we write first this summary. Note that this quantity a of k is negative. Now we come to the definition of this f of x. What is the form of f of x? Decay. We write it as kx dk. This is d of k Now this term, we introduce a of minus v e to the power minus I u x d of minus u, and the limit is from minus infinity to 0, where we have substituted k is equal to minus u. Since this is odd and this is also negative, so makes it positive, the overall quantity is 0 to infinity. This minus sign comes from the changing of limits. Where you can now change u by k. This is the second integral. So the thing that becomes 1 upon root 2 pi integration from 0 to infinity. This part is minus, this is a of k common, then e to the power I kx minus e to the power minus I kx dk. So the quantity within third bracket is, second bracket is plus twice I sine kx. So the result becomes decay, and this is the summary. This first line, this is called Fourier cosine transform. And is applicable for even functions, and it is Fourier sine transform applicable for odd function. This is for even function and this is for odd function, the simplification. One more thing, see that if fx is even and real, here we have considered f to be real. If fx is even and real, then ak is also real and even. If f is even odd, then ak is imaginary odd. This is another property of Fourier transform. Till now we have defined Fourier transform in 1D. or in let me going over to 3D, let me write the Fourier transform when the variable is not x, rather than it is t. So for the Fourier transform in position basis is 1 upon root 2, the general definition. And the inverse transformation is this. It is in x-k relation, that is when we make a transformation from x to k or k to x, position to momentum, or the vice versa. There is another transformation important, is the time frequency transformation. Here we define a of omega is equal to 1 upon root 2 pi minus infinity to plus infinity f of t e to the power minus I omega t dt. This is the Fourier transform. The inverse transformation is f of t is equal to 1 upon root 2 pi minus infinity to plus infinity a of omega e to the power I omega t d omega. Now we come to the Fourier transform in more than one dimension, that is, we consider Fourier transform in 3D. The Fourier transform in 3D, we write this equation. A, now it is a vector k, so this is 2 pi to the power minus 3 by 2 to the 2 pi to the power minus half coming from each dimension, so 3 dimensions, so it is 3 minus, then this integration is from minus infinity to plus infinity. Here f is a function of vector r, and this quantity will be e to the power minus I k dot r, and the integration is over dr. This is volume integration. Volume integration. And the inverse transformation is f of r is equal to 2 pi to the power minus 3 by 2 a of k e to the power I k dot r d of vector. It is the integration over in k space, three-dimensional k space, and decade. So this is the Fourier transform in 3D. Here, since time is has only one dimension, it doesn't have any three-dimensional analog. That's all about Fourier transform in 3D. Now we shall come to discussion of Dirac Delta function. As you have aware already, the Fourier transform of Dirac Delta function. Now our interest is Dirac's delta function. Now, Dirac Delta function, as you have already aware from your studies on electrostatics, it is defined by Dirac Delta function. Delta of x is defined by the property that integration f of x delta of x dx is equal to f of 0. To be specific, for other case it is f of x delta x minus a dx is equal to f of a when the integration region of integration includes x is equal to a. In the case of Fourier transform, we do not have to bother about the fact whether the integration limit integration includes the center of the delta function, as because the integration is of infinite extent. Now our first term will be to find out Dirac Delta Fourier transform of Dirac Delta function. So we write delta of x. First we write a of k, it is one dimensional case, so it is 1 upon root 2 pi. You know this definition, minus infinity to plus infinity. For f of x we write delta of x, then it is e to the power minus I kx dx. As per the definition of delta function, the result, this part is e to the power 0, which is 1. So this is, we have used this property, delta of x f of x dx is equal to f of 0. Here f is this function and it is at 0 is 1. So we use the inverse delta function, inverse transformation. So we write delta of x is equal to 1 upon root 2, then a of k e to the power I kx dk, integrated from minus infinity to plus infinity. We see that a of k is 1 upon root 2 pi, so this makes it 1 upon 2 pi integration over from minus infinity to plus infinity e to the power I kx dk. This is the definition of delta function in 1D. Here we have considered the delta function to have its center at the origin. Instead, if we have a delta function, this is delta at origin, this is centered at origin. At x is equal to 0. If the delta function had a origin at some other point, say at x is equal to x prime, so we write delta of x minus x prime. The corresponding ak would be integration over all space x prime. So the on integration from all limits, you will have only this. So the corresponding delta x minus x prime can be written as 1 by root 2, and this 1 by root 2 makes it 2 pi, then integration from minus infinity to plus infinity. In the definition of f of x, there will be an e to the power I kx. It will have an e to the power I kx, and this e to the power minus I kx prime comes from here, and the integration over dk. So the result is this is the delta function. So there will be lots of such relation, and we shall, as usual, we shall summarize all those so in 1D for delta x minus x prime, we have a of k is equal to 1 upon root 2 pi to the power minus I k x prime, and delta of x minus x prime is equal to 1 upon 2 pi integration over all space dk. Now, if we have the delta function in time basis, or let me write other word, for delta of k minus k prime, when the delta function is already in momentum basis, then the relation will be f of x is equal to this is k prime x, and delta of k minus k prime would be dx. The three-dimensional analogues of these are very easy. We first write the three-dimensional delta functions. We see that the Fourier transform has an intricate relation with the delta functions for delta of r minus r prime, when delta function in 3D position basis. This is x. No, sorry, it's okay. Minus 3, no 2. When the delta function is in is in three-dimensional k basis. That's all space. There are delta function in time basis. So this relation will come. And delta of t minus t prime and finally the delta function in frequency based domain. So this is the complete list of delta function in all the bases. In the next, that's all about the Fourier delta functions relation with the Fourier transform.